Hey there, physics folks. This is just a short video to post the solutions to the warm-up that we did in class today, January 10th, especially for those of you who are unable to be in class today. Two energy problems, one with a backpack lifting it up and dropping it to the floor, and a second one with a ball rolling down a ramp and reaching a maximum height. I went ahead and made a little bit larger document so that you guys could see it better on the video. And so let's go ahead and get started. So we have a 2 kilogram backpack that's lifted from the floor to a height of 2.2 meters. Calculate the work done on the backpack. Then we're going to ask to know what the speed of the backpack is when it has dropped halfway down back to the floor. So if you haven't already started doing this, again, want to draw a quick sketch just so you guys can more easily see what's going on. If you need to fast forward this while I draw mine, or stop it and you draw yours, that's fine. So here we have the backpack on the floor. We're going to raise this backpack up to 2.2 meters. We'll label that in just a second. And then we're going to drop it back down, and at some point it's going to be halfway back down to the floor, and it's going to be, of course, moving. So this distance, or this height we should say, is 2.2 meters. We know that when it's halfway back down to the floor, it will have fallen halfway, 1.1 meters, so we could label this 1.1 meters, or we could also label the distance that it fell. Either one is fine for this first part, and we know it's going to be moving at this point, so we want to know the speed when it gets to this spot. Now, the easiest way to think about this is we're doing work in the vertical dimension, okay? And so when we do work in the vertical dimension, or any dimension for that matter, we know that work is just equal to force times distance, and we use F for force and S for distance. We also could say that there's also an equation that we use that if there are angles involved, where we'll say F times cosine theta S to determine the component of the force that's in the same direction as the displacement. However, we're going to go ahead and use this equation because this is a simple problem where the force and the displacement are in the same direction. So we can just say the work done in lifting is the force that we exert, which in this case is the weight because we're lifting it straight up, and the distance, the S distance that we're going to lift it, is equal to the height. Okay? If we go ahead and plug and chug, we can say that work equals the mass, which is 2.0 kilograms times 9.8 meters per second squared times 2.2 meters. Plug those numbers into your calculator, and you should get the W equals 43.12 joules, which checks out to 43 joules at the bottom here, so we can put 43 joules in a box if you want. Okay. Now, we're going to go ahead and use this same diagram for this second part. And what many of you are probably thinking is, well, this is just a backpack falling from rest and falling down a certain distance, and we want to find the final speed. So that sounds like a typical kinematics problem. And we'll go ahead and do it as a kinematics problem first, and then I'll show you how powerful the concept of conservation of energy is. So the first thing we're going to do is go ahead and list our variables, V naught, V, A. I'm going to say Y because it's vertical, and T. You could use X, it doesn't really matter. You know it's the displacement. Well, we know the backpack is dropped from this height, so it's dropped from rest. We know that gravity is what gets it down, negative 9.8, because in this case this is an acceleration due to gravity. And we know it falls halfway down, so that distance down is half the distance, which is also 1.1 meters. Make sure that's negative because we're moving down when this happens. T is not applicable, and of course we're looking for the velocity. This gives us the fourth equation, V squared equals V naught squared plus 2AY. We know that the initial velocity is 0, so we can solve this. V equals square root of 2AY. Okay? And when we go ahead and plug and chug, I'm going to rewrite this. Square root of 2 times negative 9.8 meters per second squared times negative 1.1 meters, and we end up with an answer once we plug and chug with 4.64327, and that's going to be, of course, in meters per second. Now, if we were doing this with kinematics, we would probably take the negative of this because that's the velocity on the way down. Of course, we know that square roots are always plus or minus. Because it says speed, we can leave it as just v. That's going to be 4.6 meters per second. Okay? Now, interestingly enough, because this is the energy chapter, we're going to go ahead and solve this using energy as well. Okay? And what we can easily say is when we look at this backpack, we know that it falls down from a certain height, and we know when it falls, it has some potential energy up here. And that potential energy is equal to mgh, the work that we put into it. When it falls down a little bit farther, we know that it has some kinetic energy. But it also has some potential energy because it still is at some height above the surface of the floor that they've shown us here. Okay, so it has potential plus kinetic. Now we could also say that this potential and there's plus kinetic up here, and even though we know it's not moving, so we know it doesn't have any kinetic energy up here, but we can show that there are two forms of mechanical energy that we want to consider. Now the two chunks of energy here, the total energy, the PE plus the KE up here and the PE plus the KE here, have to be equal. The conservation of energy does not say that the PE here equals the PE here or the KE here equals the KE here. It means the total, these two totals are equal. So let's go ahead and write that down first. So let's take a look at conservation of energy. So when we write that down, I'm going to say PE initial plus KE initial equals PE final plus KE final. Now, you of course could use ones and twos or befores and after. It doesn't really matter. Your book, you should know that the textbook often puts the final energy on the left-hand side of the equation and the initial on the right-hand side. It doesn't really matter. Now, before I do any solutions or even think about what's going on up here, I'm going to go ahead and expand these values so that we can see what they are. As you recall, potential energy is mgh, and that's the initial, plus kinetic energy, which is 1/2 mv initial squared, and that's going to equal the mgh final for potential energy final, and the 1/2 mv final squared for final kinetic energy. All right. Now, we already mentioned that because it starts from rest, and we know that this is at rest up here, we can pretty much assume that the kinetic energy at the top is 0, okay, because it's not moving. We further notice that everybody brought mass to the party, so we can cancel the masses. Even though that one's 0, that mass also cancels. And so what we're left with is an expression that just has g and h, and 1/2 v squared. Now I'm going to do something further that you might not be comfortable with, but I want to talk about it nonetheless. And I'm going to say that we know that this backpack gains kinetic energy because it falls through a certain distance and it loops. Now the change of potential energy is the change from this position at the top to the position that's halfway down. And the reason the potential energy changes, of course, is because the height changes from an initial height to a final height. Now, I want to submit to you that when we first start out, it's at 2.2 meters, and it ends up at 1.1 meters. So the height initially, that would be this height, is going to be 2.2 meters. The final height is going to be 1.1 meters. The change in height is really this distance here. Now that happens to be 1.1 meters as well, but the most important thing that you want to look at here is if we say that all we care about is this first part here, this top part, I'm going to draw a line here and I'm going to pretend that that is my new 0 point. That's my new reference point. Now you might not be comfortable with that because of course you'd say it has potential energy here, and if I call this 0 then it has no potential energy. But remember, what we're concerned with is the change in energy. And if we want to know what the change in height is, it's really 2.2 minus 1.1, and that is this height, and we know I'm going to go ahead and label that as 1.1 meters. And I'll come back and prove to you that that works, no problem, but let's just go ahead and go with this for now. So we know that this is 0 meters high, so I'm going to say that this is 0 too, because the final height I'm calling 0 according to my new reference. Now I'm left with an equation that looks something like this. So we have GH naught equals 1/2 V final squared. And when I solve for this, I'm going to end up with an expression that says V equals square root 2G H naught. Okay, now I'm going to go ahead and circle these both in a red box. Well, not both, but I'm going to circle this in a red box. And then I'm going to go back up here to my kinematics problem, and I'm going to circle this in a red box. I want you to take a look at that. Pause the video if you need to. But make sure you understand that even though these are using different variables, these are saying the same thing. Okay? This is 2ay, square root of 2ay. This is square root of 2gh. Now let's recall that y in this case is the displacement in the vertical dimension, which was negative 1.1 meters. In this equation, that's the same as saying h naught. And h naught is the initial height above our arbitrary reference point that we marked in here. So that's 1.1 meters. That's the same height. We can also see that the g in this case is the acceleration due to gravity that we were using to calculate the weight force. But let's not forget, up here we used a as negative g for the acceleration due to gravity. So these are the same two expressions. So kinematics works for this problem, so does conservation of energy. That's true for many problems, but it's not always true. So we're going to have to take note of that, and we'll take a look. Well, let's go ahead and first plug and chug and see what we get. So this is going to equal root 2 times g, which is 9.8. It's positive in this case, meters per second squared, times, what's h? The h is going to be 1.1 meters. And when we plug and chug, we should get, wow, what do you know? It's the same answer. We don't even need to calculate it. We're going to get 4.64327 meters per second, which of course rounds to 4.6 because it's, 4.6 is the same number. Now that works because, of course, kinematics and energy can both be used for this problem. If you're not comfortable with this zero, setting an arbitrary zero, let's just pretend like we didn't do it. Okay, let's just pretend like we didn't set that arbitrarily to 0. Now, in order to do that, I'm going to redo this equation, and I'm going to redo this solution, but I'm going to use energy again. But let's take a look. So first, I'm going to go ahead and say at the beginning, PE initial plus KE initial equals PE final plus KE final. And when I go ahead and do that, I know I'm going to go ahead and cross out first the KE initial because it's not moving, that's 0. But now I'm going to leave the final potential energy because we said we're not comfortable with making this 0. So let's pretend that we wanted to leave it there. So even if we do that, we're going to get mgh initial equals, mgh final, whatever's left over for the potential when the backpack is here, plus 1/2 mv final squared, which of course is the speed that we're looking for. If you go ahead and say yes, certainly, again, everybody brought mass to the party, and we go ahead and solve for v, you can see that we're going to get rid of the 1/2. We're going to end up with v is equal to, check my algebra if you want, is going to be 2g, which is going to factor out, times h, whoops, this should be h final, pardon me. It's going to be h initial minus h final. Now, I know in my previous expression, I had 2gh initial. And the reason I had that was because I got rid of the final potential energy. Well, even if you leave the final potential energy in, okay, even if you leave the final potential energy in, you get a similar expression. It's just h initial minus h final. But if we go back up to our backpack, we can see that h initial minus h final is the same 1.1 meters. Okay, that is the same number. So it works either way, whether you set your 0 point down here or whether you set your 0 point here. And the reason we can do that is we can define the system however we need to so that we can solve the problem for what is asked. And all they ask for is the change in energy, or we need to focus on the change in energy from the top of its path to halfway down. Okay, that's it for the first part. Let's take a look at the second part in the next video.